Hi, everyone. I'm Andrew Miklas, CTO and co-founder of PagerDuty.com. And this talk is about some of the techniques that we use to make sure that PagerDuty is always available and ready and able to wake you up at 2 a.m., even if you secretly wish that we weren't. So to understand why reliability is so important to us, you have to know a little bit about what our product does and the team that built it. So I hope you all won't mind if I give you the elevator pitch. So PagerDuty is basically an alert dispatching system for IT professionals. We collect problem reports from your monitoring tools that you've already deployed, aggregate them, and then assign them to engineers by consulting user-defined schedules and on-call escalation policies. And then we make sure that the responsible engineer knows about the problem by placing automated phone calls, SMSs, and emails, sometimes repeatedly, until the person picks up and is able to address the issue. So we're used by big and small companies across a variety of verticals, including hosting, SaaS providers, and media companies. But what all of these companies have in common is that they need to find out fast if something goes wrong with their infrastructure. And that's essentially what they pay us for, the promise to send an SMS or to place a phone call within no more than 3 minutes of when their on-call policy says we're supposed to. So then you can see how PagerDuty's technical challenges are perhaps a little bit different from most tech startups. Many startups are focused on scalability, which basically means making sure that they don't hit the wall when they're trying to add their million-and-one user or account. And reliability and correctness are perhaps a little less important for these companies. Losing an upvote here and there is far preferable to having massive downtime when you're trying to add new users. But in contrast, at PagerDuty, we strive to make sure that no alert ever gets delivered late, let alone lost. So I think it's also important to know a little bit about the people that make up PagerDuty to understand if our approach to reliability can translate to your organization. So the first thing is it's still very early days for PagerDuty. So for illustration, we have 17 employees total, 10 engineers, and we're all located on the West Coast, so in the same time zone. And our small size means that we aren't able to use some of the traditional approaches to reliability that might be used at larger businesses. So for example, we don't run a 24-hour NOC where somebody is always keeping watch on our systems. We also don't buy specialized hardware or software licenses like super high-end clustered Oracle rack stuff to keep our things going. And as a result, a lot of our reliability ideas that we're going to be discussing here are especially useful for small businesses. However, they probably have implications as well for larger businesses. So high availability basically comes down to two things. First is reducing the probability of failure that leads to downtime. So when you hear the phrase MTBF, or mean time between failure, this is what people are talking about. And the second thing is accepting that no matter what you do or how many precautions you take, you're always going to have some potential for failures that lead to downtime. And at that point, the trick is to make sure that you can get your systems back online as fast as possible. And this is what people mean when they're talking about MTTR, or mean time to recovery. And so achieving high availability involves optimizing both of these metrics. And we've done a lot of work at PagerDuty on both sides of the equation. And I could go on for hours kind of about either of those points. But to avoid boring you all to tears, I've just selected one topic from each of these categories. So on the increased MTBF front, I'm going to talk about how we do redundancy at PagerDuty. And specifically, I want to talk about why failover is really not a great strategy for redundancy. And instead, what you should be using is an active-active approach or a fully distributed architecture. And on the decreased MTTR front, I want to tell you about basically how we've structured our on-call process at PagerDuty. And some of the topics I'm going to cover are what sort of metrics you should alert on, how to localize problems at 4 in the morning, and what to do about those problems the next morning. And the big idea kind of in this half of the presentation is that I want to explain that a well-run on-call process is really necessary to minimize your MTTR. So the first thing to understand when building reliable systems is that stuff fails. The servers running your applications might have their power supplies die. The disk containing your database might grind themselves to dust. Your entire data center might suddenly lose its internet connection. And your SMS provider might suddenly go offline. And so for every component that can fail, you have to ask yourself, is the time that it would take me to replace this more than I'm willing to go without it? And the answer to that is usually no. And even in today's world of cloud-based hosting, with its fast provisioning, if you want to have sub-minute downtimes, or no downtime at all, you're still going to need to have at least two components provisioned of any sort of piece of your system that can fail. So the normal way to deploy redundant systems is in a failover configuration, right? So you have one resource that handles all the requests under normal operation, and that's, we call that the master. And then you have an identically configured resource that can take over for the master if it fails, but it usually does nothing else other than just kind of track the master's progress. And we'll call that the slave. Now, sometimes you can actually have the slaves do useful work. For example, in some DB applications, you can use the slave to serve pure read requests. Now, on the failover master, what you do is you promote the slave up to the master role. And kind of the key concept with this architecture is that the master and the slave roles are very different from each other. The system is not homogeneous. So just to make things more concrete, let's take a look at how failover works in MySQL. So here we have an app doing read and write operations to a MySQL server. And because this application requires high availability, we'll set up a MySQL slave and stream all the writes done on the master to the slave. And because this is MySQL replication, we can actually use that slave to do various read-only transactions if we don't care about the possibility of them seeing stale data. And this is especially useful for kind of analytics and the like. Now suppose that your master suddenly dies. And as you might guess, this is not so good for our highly available app. Now to restore service, we're going to disconnect our slave from the dead master and promote it to the master role. And we're then going to point our app servers to the new master. Next, we're going to want to disable our analytics jobs that are running against what used to be the slave. Presumably, the reason we broke those out in the first place is that our master server wasn't powerful enough to run both OLAP and OLTP workloads at the same time. OK, so at this point, the disaster's been averted, and we can start to breathe a little easier. But not too easy, of course, because if the new master dies, we're back in hot water. So we're going to want to set up a new DB slave as soon as possible to get that safety cushion back. And of course, we can't forget to get those analytics jobs running again, because our marketing department's going to be really upset if they miss their daily conversion reports. So the nice thing about failover is that the strategy is actually really easy to understand. Now, it's not easy to execute, as we just saw. There's a lot going on there to handle failure, but it is kind of simple to understand. In fact, the redundancy strategy is entirely orthogonal to the normal operation of the system. Clients connect to one place to submit their requests, and while that place might change in the event of a failover, there's only one of them at any given time. And so basically, the service behaves as though there were no redundancy, right? You don't need to consider tricky distributed systems problems because all of the computation is just taking place in one spot. And so you do have to stream copies of all of your operations from the master to the slave, but that's almost an afterthought. And in fact, in a lot of systems, it was added after the fact. Postgres, for example, only got streaming replication support at version 9. In fact, in a lot of failover systems, the failover aspect is so separated from the rest of the system that you can actually layer it on with totally separate software. So for example, using the Heartbeat and Pacemaker projects and DRBD and virtual IPs, you can actually build failover load balancers. You can set up failover between pairs of mail servers, queuing systems, file servers, database systems, basically whatever you like. However, failure actually has some really serious drawbacks. So first off, when a failure occurs, it's going to cause downtime. Any sort of flip is realistically going to take on the order of a few seconds. And during that time, no requests are going to be processed. In fact, a few seconds is pretty optimistic for a failover design. So consider using a database, or consider a database where you're using kind of block-level replication to handle failover. So to failover in that case, what you're going to have to do is play back your file system journal on the slave, then start up the database, then play back the database journal, and you have to do all that work just before you can actually start to handle new requests on the slave. And that can get you up into the minutes or 2 minutes or more downtime right there. And also, you have to consider the time it takes to tell your clients about the flip. So updating a network or a service registry is usually pretty fast, but it's not instant, and you still have to kind of restart the apps or send them a HUP or something to let them know that they have to check to see where they should be sending their transactions to. But if you have to use DNS updates, well, that's even longer, because now, of course, you have to wait for the TTL on your records to expire. And for some clients, that even longer than that, because they don't respect the TTLs. So second, in many failover scenarios, once you start, you can't really abort it. One reason for this might be that you've actually terminated the master as part of a shoot the other node in the head protocol to prevent split brain. Or you might find it's just faster to press ahead with the infrastructure changes rather than trying to undo everything to get you back to where you were before. And finally, interrupting failover midway is very prone to leaving the system in an invalid state, which can cause some real problems, which I'll talk about in a few minutes. And third, even when failover works perfectly, it can cause drastic changes to the system's overall performance. So for example, or the reason why is because a DB server that was doing nothing a second ago and thus has nothing cached is all of a sudden hit with your full load. And as a result, things are not going to be normal for quite some time. And so these concepts combined imply that failover is sometimes not the right decision in a given circumstance. That is, doing a failover actually is going to cause you to be down longer and have more serious performance impacts than if you had just kind of sat on your hands and done nothing and waited for the problem to go away on its own. But the problem is you can't actually know that until later. Precisely when to do a flip, therefore, becomes something that you have to exercise judgment on. And just kind of as a personal observation, ops engineers in the heat of the moment tend to delay, I think, a little bit longer than they should before they hit that flip button. Whereas auto-flip scripts, or I suppose the engineers who configure them, tend to be a little more aggressive at setting off a flip operation. Now, those are the problems with failover when it works right. You can kind of think of them as the price of admission. That's the best case scenario. But where things get really scary is when stuff goes wrong. And with failover, it often does. And the problem is that failover necessarily involves making very big changes very quickly across multiple components of your system. And it's very easy for something to go a little wrong and your system to end up in a state that you didn't anticipate. And because you're making so many changes so quickly, any small deviation tends to snowball. And this causes your system to end up somewhere very different from where you expected. And if this happens, kind of your best scenario is that your system goes offline until you can figure out how to get it all back. But if you're really unlucky, your system can enter a state where the two machines basically are masters at the same time. And this is what's meant by the term split brain. And recovering from this problem can actually take hours. And during that time, you might actually need to shut everything down to prevent further corruption while you sort of reconcile two masters to each other. So I want to emphasize that this isn't a theoretical problem. Anyone who's spent any time at all with automatic failover systems will have at least once seen the automatic failover do something unexpected. And there's nothing scarier than watching your database fail over from one machine to another and then kind of get stuck in the middle of that process and not know why. Because it's going to take you a while to figure it all out and get your systems back up into production status. As an aside, it's also super frustrating when you realize that the mess that you were in was caused by nothing more than a little bit of minor packet loss that for some reason set off your automatic flip. So I actually kind of think of failover as a little bit like a pill that cures your disease 90% of the time, but makes you drop dead the other 10% of the time. And I really don't like that uncertainty in my infrastructure. So I was trying to figure out, what the fundamental problem with failover is. Why does it seem to suck so badly? Software, all kinds of software, does all kinds of complicated and hard to get right stuff all the time. So why would this be any different? And here's my theory as to what the problem is. First, you have no idea if the failover process is going to work right until you test it. But really, that's the same as anything else. You don't know whether any software is going to work right until you test it. But here's the problem. You ultimately can't test failover properly. I mean, sure, you can set up a test environment and pull the plug on one DB server and make sure that the other DB server takes over. And you're going to get that working no problem. But that isn't enough, because you need to know if it's going to work in a production environment. And this is a lot more tricky. You basically have to set up a test environment that you confidently believe captures all of the nuances of your production environment, and keep that environment up to date with conditions that changing in production, and then test against that environment all the time. And you're probably not going to be able to do all of those activities. So to be able to test your failover process, you're going to have to test it periodically in production, which is to say do flip drills. Now that sucks because you're going to cause downtime at some point during these tests. Now, that's downtime for a good reason. You're basically causing a little bit of downtime in a controlled way. and at a time of your choosing to prevent kind of big downtime at a later time under conditions that you don't control and at kind of an inconvenient moment. But that still really sucks. Now, if this were the end of the story, if it was just like, okay, do production flip tests and you'll be fine, I could probably live with failover. But even that isn't enough, because the system that you're ultimately going to be executing flips against is going to be perturbed in some way, right? And that's why you're flipping in the first place. And you need to be able to test, essentially, your flip process against not just a production system, but a production system that's been perturbed in every conceivable way, to make sure that it's going to work right. And so by perturbed, I mean things like, your production being under abnormally high load, or, a production system where you're kind of having brownouts, where the machine is attaching and detaching from the network, taking a few transactions, then stopping, and then taking a few more. Now, the problem is that the state space of a system that's well-behaved, everything's working right, is really big. And it's hard, but it's possible to reason about a system that's behaving correctly. But the state space of a system that's gone off the rails is essentially infinite. And as a result, they're pretty much impossible to reason about. And I think that's why you can't actually get failover to work reliably. So I'd like to go through an example, just in case I haven't convinced you. So on September 10th, GitHub went offline for about an hour and 46 minutes. And they had about another hour after that of degraded performance. And they were very kind, and they wrote a postmortem about this event. It's actually really interesting reading, and if you haven't had a chance to check it out yet, definitely take a look at the URL at the bottom of that screen there. Very, very highly recommended. Oh, and by the way, this example isn't meant as like a kind of a jab at GitHub. I just thought they had such a great postmortem describing this exact situation that I couldn't resist using it here. But to summarize their architecture, they have a DB cluster consisting of 3 servers, 1 master and 2 slaves, with the roles of the servers managed by an automatic flip tool called Pacemaker. So our story begins with an admin kicking off a long-running migration against GitHub's primary database. And this causes the load on the DB server to spike, and as a result of that, the server stops responding to its heartbeats in time. And what happened here was that the high availability software decided that the master was broken, and it initiated a flip by promoting one of the slaves to the master role and repointing the app servers to point to the new master. And at this time, it also adjusted the replication topology of the cluster so that the 2 slaves properly tracked the new master. Now, the newly promoted master server took over, but it had a cold cache because it wasn't doing anything prior to the flip. So it, or expectedly, kind of didn't really do so well with the increased load. So it too began to miss heartbeats. And the autoflip software decided that the best course of action would be to stop using that server, so it actually repromoted the old master back into the master role. Now at this point, one of the ops engineers saw what was happening and decided to turn the autoflip mechanism off. So let's see how this compares so far with our complaints against flip architectures. So first, we can see that the flip indeed did behave very differently in a perturbed production environment than it did in test, right? So consider this oscillation problem, where the cluster would detect an issue, correct it by flipping to the slave, only to see that the issue got worse, and then correct for it by flipping back to what was the master. This isn't something you're going to test, or going to be able to find in ordinary tests. And in fact, you might not even find it under ordinary production tests. You'd have to be testing under a situation where the DB was under a very high strain, maybe running a migration, basically test the exact scenario that happened here. But even without the oscillation issue, flip is not the right answer in this particular case, because here we have what's mainly a performance issue. Flipping caused the cache to go cold instantly, which is not what you want to do when you're having a performance problem. And the problem here, though, is that autoflip software can't, in the general case, tell the difference between a slow system and a non-responsive one. OK, so back to the story. So after disabling the autoflip, one of the slaves was actually left replicating from what once was, but wasn't any longer, or isn't any longer, the master. So in other words, the system as a whole was left in an unexpected state. And this caused some read-only queries to be answered with stale data. Now, when this was detected, ops responded by re-enabling the autoflip software. And I think what the idea here was that it would pick up where it left off and kind of repoint the slave to the correct master. But instead, the autoflip software hit a bug and crashed, but not before triggering a new master election. And the result of that election was that the out-of-date slave was actually promoted up to the master role. Now, this isn't exactly split brain in the classic sense, since we never had 2 servers thinking they were both mastered at the same time. However, we do have a situation here where DB server A and DB server C each have transactions that the other doesn't. And so other components of the system never expected that this would happen. And as a result, the system was now in a corrupted state. And in fact, that corruption resulted in security violations. So people, for a very brief period of time, were able to kind of see commits and things that they weren't supposed to be able to see. So what happened here was that the flip software took the system to a state that was slightly outside of what was expected. Specifically, a slave was tracking a server that was no longer the master. Now, the manifestation of this bad state started just as a stale slave, right? And a stale slave is not a big deal. Slaves fall behind their masters all the time, and it's something that would have been considered in the design of the system. However, a slave tracking the wrong server probably wasn't something that was anticipated by the autoflip script. And so when it tried to continue, it drove the system even further outside of its correct state and eventually caused data corruption. So the question here is, what's the lesson we're supposed to be taking away? Was it that they didn't test enough? Now, I don't think that's the case. I think it's not practical to test how a system is going to respond to a flip under every possible scenario. And even if they didn't think to test the autoflip software against a DB server that was running a gnarly migration, would they necessarily have thought to test the autoflip software against a cluster that had been previously incompletely flipped and thus was, had a broken replication topology? So instead, I think what we have to do here is look towards different approaches to redundancy. Specifically, one that doesn't involve us to make a series of, doesn't require us to make a series of drastic changes to our infrastructure in an emergency, where any sort of a misstep is going to cause ruin. So the solution is to design systems to be distributed from the outset. And by distributed, I mean a system where all of the nodes are active under normal conditions. An incoming request can be routed to any one of a set of nodes. You might even route an incoming request to multiple nodes simultaneously for performance or fault-tolerant reasons. So if you're designing for reliability, a key factor that you're going to want to consider is the homogeny between the nodes. So at a minimum, you're going to want to make it so that you have no difference between nodes. Nodes might self-elect a master, a leader, or something like that. But from your perspective and the perspective of your clients, you don't need to understand this. You just submit your request to any node, and everything works itself out. But even better, though, is a system that internally doesn't have this distinction. So the problem here is that leader elections and the like are still a sort of failover. And they're much more constrained, and they're better tested, and they're less likely to fail than infrastructure-wide failover. But they're still failovers nonetheless. So to give an example of a system that kind of fits that second criteria, this is how Cassandra, a distributed database, goes about storing and retrieving data. And so for any Cassandra experts out there, I'm going to describe the behavior of a 5-node cluster with a replication factor of 5 and quorum reads and writes. So the app begins by submitting a write request to any node in the cluster. And the receiving node then forwards that request on to all other nodes in the cluster. And once it confirms the write with at least 2 others, which in this case happens to be nodes 2 and 5, it can return success to the app. The writes to nodes 3 and 4 can actually continue asynchronously without fear of data loss or inconsistent future reads. So now, let's say we have a data center failure, and that knocks out 2 of our nodes. This actually isn't a problem at all, because 3 out of 5 of our replicas are still up. Now let's say that our app needs to actually read back the data that it just wrote. So the app can submit its request to any surviving node, and that node will verify its data with the 2 other nodes in the cluster to ensure that it isn't serving stale data. And then, once it gets confirmation, it'll can pass that data back to the client. So the main benefit, then, of a distributed system over a failover system in terms of reliability is that in a distributed system, the failure of a node is not an unusual situation. So think about BitTorrent. Nodes join and leave the swarm all the time, and the system is designed from the ground up to support that. And this is a very different mentality when compared to the loss of a master in a MySQL replication setup. In a distributed system, handling failure doesn't require a complicated series of operational gymnastics to go exactly right, nor does it require us to run rarely executed and therefore not very well debugged failover code to kind of get the system back into a usable state. In fact, baking the idea of failover into the system as an everyday occurrence gives us a number of very important reliability wins. First, the failure of a node often causes no downtime at all. Clients just have to try the request again on another available node. And second, the system's performance during a failover tends to be much smoother, or the system's performance during a failure tends to be much smoother, and more in proportion to the number of affected nodes relative to the size of the cluster. So consider a distributed database. Instead of having the entire system's cache go cold when you lose a node, you instead just lose a small part of your cache. And for the most part, the system can just keep going. Most importantly, though, there's a lower risk of catastrophic failure. And this is because there's just fewer things to do to handle a failure, and thus there's kind of less likely to go wrong, or less likely for stuff to go wrong. And so as an added bonus, actually, dealing with most sorts of maintenance issues becomes a lot easier. So if you need to roll out a new kernel, well, that's no problem. Just apply the update, reboot the machine, and probably no one's going to notice anything. So these benefits come at a price, though. Distributed applications are hard to build because you have to think about failover, or you have to think about failure all the time. Now, with failover, remember, you could think about the error case as being separate from the normal case, right? The system is either operating correctly on node A, or it's operating correctly on node B, or you're in the process of moving from node A to node B. But with a distributed system, you don't have that luxury. You have to be considering both nodes as active all the time. Now, you can actually sidestep a lot of the complexity of dealing with a distributed system by making your application tier stateless and using a distributed state layer written by the pros. And this is a little bit analogous to using a DB to store all of your state. If you do it right, it'll actually handle a lot of the heavy lifting for you with respect to ACID compliance and that sort of stuff. But the downside is that many of these systems, like the ones I've listed here, don't provide all of the niceties of a full database. So for example, there's no real transaction support in any of these systems. So currently, a lot of PagerDuty's infrastructure actually does rely on the failover approach. But we've learned from experience that this doesn't give us the reliability that we want, at least in our alert dispatch pipe. So we're now actually looking at porting our dispatch pipe to run on top of Zookeeper and Cassandra. And so far, things are actually looking very well, or things are working out really well for us. However, it did take us quite a while to get used to working with a data store that doesn't have transactions. You have to be very careful with how you sequence certain operations. We're also evaluating using Percona XtraDB cluster with locking managed by Zookeeper as kind of a drop-in replacement for MySQL for our non-alert dispatch related systems. And the advantage to this solution is that we only have to make slight changes to our code. But the downside relative to using Cassandra is that the performance isn't as good in the normal case, or even in certain error cases. So I think the overall lesson kind of I want to communicate is this. Whenever possible, prefer active-active systems and designs to active-passive. I think you get much better reliability out of active-active systems. Another way to put that is distributed systems. They're not just for scalability. Okay, so this is kind of the second half of the talk. And sort of, one of the things that we mentioned before is that you can do everything possible to increase your mean time between failure. And as we were discussing, you can have lots of redundancy and take great pains to set everything up right. And you can do, code audits, static analysis, extensive QA processes before deploying, like anything at all. But sooner or later, you're going to have a problem in production. And things are going to go wrong that either weren't foreseen or were too complicated to have an automatic response to. Now, if you're okay with being down from a Friday evening to a Monday morning, and that's about 64 hours, you can probably get away with just sending off an email to your sysadmin or ops engineers if anything goes wrong. But otherwise, you're going to need to have an on-call team. So at PagerDuty, we like to think of our on-call process as having 5 distinct stages. So first, our systems have to automatically detect that there's a problem. Second, our systems automatically generate an alert and route it to the appropriate engineer. And third, that person who got the alert has to determine the cause of the problem. And that's actually the first point in our system where a human is involved. Fourth, the problem needs to be fixed. And finally, after the emergency is over, we have to analyze what happened to see if we can prevent similar occurrences in the future. So let's look at each of these steps in more detail. So ultimately, the detection phase comes down to ensuring that some sort of metrics stay within an acceptable range. And the question is then, okay, well, what metrics should you feed into your on-call system? Now, there's no general answer to that question, but something that we found important to do is to alert on a mix of high and low-level metrics. So low-level metrics are things like host metrics, so load average, disk space, CPU utilization, memory usage, that sort of thing. And application level metrics, we also consider low-level metrics. So this is things like message queue lengths. These are easy to set up, and many monitoring systems will actually generate alerts on these metrics automatically. And these are useful because when they go out of bounds, you know exactly where to start looking. They're a little bit like the unit tests of the monitoring world in that respect. The problem is this. It's very possible to break your site without causing one of these metrics to go out of bounds. So I've seen actually a case where an e-commerce retailer broke their order pipeline. They basically deployed code that caused 500s to occur on the last stage of the checkout pipe. And they did this deploy very late on a Friday afternoon. The problem was that their monitoring was based completely around low-level metrics. So they had lots of tests to say things like, okay, can I connect to the web servers? Are we taking connections on port 80? Are the machines, do they have enough memory? Is the load average at where it should be? But they didn't have any high-level metrics. So as a result, they didn't realize that they weren't accepting orders until their support guys came in Monday morning, and they noticed a huge pile of tickets that basically said, well, we tried to give you money on Saturday, but we couldn't because we got a 500. So the solution to this is to set up monitoring on high-level metrics. Now, these aren't as easy to set up because they're going to be different for every business. You can't just use out-of-the-box software to kind of get them going. And what you want to do when you're defining these is to think about how to measure whether you're doing right from a customer's point of view. So for example, at PagerDuty, we use the number of outgoing alerts now over SLA and the number of connect failures to our API endpoint in the last 60 seconds. I've seen an e-commerce vendor, not the one I was just talking about, actually define a metric that was sales per 5 minutes. And essentially, they knew exactly how much money they should be making right now, taking into account the day of the week, the hour of the day of the year, and kind of expected growth that they had versus last year at this exact same time. And if they weren't making exactly what their models said they were supposed to be making, somebody would be dispatched to figure out why. And the nice thing is once you have a few of these defined, you're set, right? Because no matter how weird the specific cause is, if you do something to damage your business metrics, you're going to find out fairly fast. In this respect, monitoring on your business metrics is a little bit like running integration tests, right? When they break, something's gone wrong, even if you don't immediately know what specifically the problem is. So there is one downside, though, and that's you don't find out about problems until they've started to affect your bottom line. So in contrast, low-level metrics can actually be used to find out about problems before they start to affect customers. So, if you look at the advantages and the disadvantages of each, you see why you really actually have to have both low and high-level metrics feeding into your on-call process. They each kind of serve a different purpose. Okay, so now that you've determined that a problem exists with your system, you need to get the word out to an appropriate person, right? So the things that you need to consider here are, well, who should be called? So you want to make sure that alerts are routed to a person who can take action. And this basically means alerting somebody who's both knowledgeable about the broken system and someone who's going to be in a position to fix the problem at the time that they're paged. Because there's nothing more annoying than getting woken up about a problem and then simply having to forward that on to somebody else because you don't have the expertise to solve it yourself. Another big problem is getting a call, for example, while you're on vacation, and then having to call a coworker while you're roaming to make sure that somebody knows about the case. So another big thing that you're going to want to consider is how many people should be called. And I think usually the answer to this question is one person. The problem with sending out too many simultaneous alerts is that it muddles who owns the problem, and thus who's responsible for ensuring that it gets fixed. However, for very serious issues, it can sometimes make sense to simultaneously contact more than one person. And while one person should still own the problem, having extra hands on deck can help the problem owner kind of debug faster. It can also be useful to have more people available when searching for solutions to kind of previously unseen issues. And finally, a question that something that you'll have to figure out is how long should you wait for someone to acknowledge that they've been assigned an incident before escalating on to somebody else? Now, there's no general answer here. It's going to depend, again, on the severity of the alarm. But whatever you decide, you'll have to make sure that it's consistent with how you've set your alerting channels up. So for example, SMS delivery times are extremely variable. And even ignoring that, you have to give people at least a minute to kind of unlock their phone, read the message, send a reply, and then have that reply work its way through the network back to us. So as a practical matter, if you need tight escalation timeouts, you should really strongly consider using phone alerts. Okay, so you've detected a problem and alerted the appropriate engineer, or rather your systems have, because up until now, everything's been totally automatic. What now? Well, first you need to find the cause of the problem. And if the alert is due to a high-level metrics violation, it often isn't obvious where the problem is. With a low-level metric violation, you'll often want to start looking, basically in the component of the system that is now has an out-of-range metric. However, even in this case, it isn't always obvious what happened. So for example, a failed system will often cause alerts to be generated that are related not just to it, but also to all of its dependent systems. And you should try to avoid that when you set up your alerting mechanisms, but sometimes it happens anyways. And this can kind of cause you to get that effect where it's like your whole alarming panel kind of lights up at once because you've got like a network problem in like a core router or something like this. It can make it very hard to kind of trace down and figure out what actually caused all of those errors. The truth gets kind of lost in the noise. So one way you can trace down the source of a problem is to open up a browser tab for each of your favorite monitoring tools and SSH into some of your machines, and then start manually poking around to figure out what the problem is. But from painful personal experience, I can tell you that this really isn't what you want to do. Instead, what you do want is to have a nice dashboard where you can go and see your key low-level metrics, a simple up and down readout for all of your hosts and services, and information about any anomalous objects in your system. So for us, for example, this would be alerts that for some reason are stuck and we're not making progress sending them out. You basically want to have this page because you want to be able to get a good idea of where the problem is without even having to click the mouse. You just kind of glance at it, come up with your theory as to where the problem is, and then, once you've got an idea of where to start to dig, then you can bring out the heavy-duty tools to go in deep. So once you know what the problem is, you're likely going to have to run some sort of procedure to fix it. So you could have your engineers at 4 a.m. trying to devise a response to this problem. But also, from painful personal experience, I can tell you that the one thing you really don't want to have to do too hard at 4 in the morning is think. So to the greatest extent possible, you should think through how you're going to respond to problems and write it down beforehand, which is to say make an ops handbook. Cover things like, okay, here's how you flip the database, right? If you've decided to go with a flip architecture. Or here's how to prune incoming events out of the event queue. So, and by the way, you should consider strongly keeping this information in a wiki. It really helps to keep it up to date if anyone can kind of go in there and edit quickly based on what they've found happened last time they tried to run that process. So a rule of thumb is also, really avoid forcing your engineers to have to SSH into a system to fix common problems. It's slow and it's super error prone at 4 a.m. And you'll find that even your most senior engineers are going to forget the various flags and parameters to all the Perl scripts that they've written months ago to handle this very problem. Again, just at 4 in the morning, you're not, what is it, -W, -S. This has happened to me. It's really not fun. So instead, what you should really do is spend time to build a nice GUI to execute your most commonly needed ops actions. And the idea here is that when something goes wrong, all you have to do is go to an admin web page, and then there'll be kind of a nice little list of command buttons there, and that present you with a palette of common operations actions you can take. Okay, restart this service, restart that service, or prune out this event queue here. All just kind of as a little list of command buttons there. And this is way nicer than having to manually type in cryptic commands or copy and paste from your ops handbook. Just a word of warning, there's a small tendency for the usability of internal systems to get sort of ignored. And I think it's really important to not fall into that trap for your dashboard and your other emergency response pages, because there's really nothing more annoying or frustrating than misinterpreting a graph at 4 a.m. and realizing you've been off on this wild goose chase to solve a problem because the axes on a graph were written too small and you thought it said something else. Again, personal experience. Another problem is accidentally hitting the wrong command button on kind of your ops master control page, and then realizing you're going to have to be up for another 30 minutes to undo some problem that you just caused by kind of slipping and hitting the wrong button, then wondering why there wasn't like a confirmation dialogue on that. So the thing to remember here is that these pages, they're not meant for consumption by your engineers. They're meant for consumption by your engineers at 4 in the morning. And you'll find that your engineers at 4 in the morning are like very different people. And so finally, sometimes you're going to encounter problems that you haven't anticipated and for which there is no obvious fix. So you're going to have to improvise. So the key here is to be proportionate in your response. So you don't want to take high-risk actions to fix a problem that's only affecting, or maybe posing just a minor inconvenience to a handful of customers. Unfortunately, in the heat of a moment, I think there's a tendency to overestimate the severity of problems. So you're going to want to be very mindful of that. Something that we've done is we've designated certain high-risk actions, such as failing over from one data center to another, as being only acceptable when we're operating at a given severity level or higher. Okay, so fixing a problem isn't the end of the story. You should be periodically reviewing your paging logs to identify the issues with your system that most frequently cause pages, and then working to fix them. And this is actually really great for morale. Nothing makes me happier than when we roll out a change that's going to eliminate like a bug or a certain class of performance issues, which I know I've been woken up many, many times in the past about. And you should also be looking for ways to improve the on-call process itself. So, for example, are you contacting like 5 engineers every night in response to like a minor problem? So if so, you're probably over-alerting. And actually, in that case, if it's the same problem every night, you probably also really should get that problem fixed. Another example is, do alerts constantly escalate past some people? Perhaps your escalation timeout then is impractically set too low, or perhaps some people need to be reminded to keep their phones off vibrate when they're on call. So for very serious problems, actually, doing formal postmortems is super useful. And the overall goal with these postmortems is to prevent similar future disasters by figuring out the most efficient way engineering effort could have been spent to eliminate the possibility of this particular incident that just occurred. And this involves tracing the entire chain of events, starting from the disaster itself and going all the way back to the initial design of the system. Now, most disasters have more than one cause, and sometimes the easiest way to prevent a similar occurrence from occurring in the future isn't going to be the most obvious one. And so postmortems then help you choose between the best possible fix rather than the one that might just be first popping into your head after a more shallow or even non-existent analysis of the issue. One small request, though, if you do actually do postmortems, consider sharing the results. Because I think, by and large, we all face the same sort of problems, and that being able to read through basically how other people approach their versions of our problems is really very useful. And speaking of which, now would be a really good time for me to thank GitHub for the postmortem that I referenced a few minutes ago. It was certainly very helpful for me to kind of crystallize some of my thinking about failover and distributed systems. And one final suggestion, make sure that your engineers spend at least some time on call. I think this is the easiest way to make sure that operational deficiencies in your app get fixed. So in my mind, this is kind of the key concept behind DevOps. If you want your developers and operations engineers to get a greater appreciation for each other, have them work together to solve ops problems. I think it's also a really great way to have them build respect for each other, right? Nothing builds, strengthens those bonds than facing kind of shared adversity. So I guess here are kind of the main takeaways from my talk. First, avoid using failover as your redundancy strategy. And instead, if at all possible, prefer using a distributed or an active-active approach. Second, monitor your systems with a combination of high or business metrics and low-level metrics. They both serve different purposes, and you really can't replace one with the other. Third, build nice dashboards and control panels for your operations engineers, because really nobody wants to work with a CLI at 4 in the morning. And finally, constantly be reviewing and improving your on-call process. Okay, and with that, I'd be very happy to take your questions. But before I do, I just want to point out that we're hiring for both our San Francisco office and our office in Canada, which we're trying to figure out whether to put it in Vancouver, Toronto, or Montreal. So if this sort of stuff interests you, please really feel free to drop me a line. Thanks. I think there's a mic working its way.
So your idea of using the GUI and presumably a big red button to fix stuff at 3 a.m. I'm kind of curious what your thoughts are on going that one extra step further and just making it fully automated.
Yeah, so I think that's totally what you want to do in most cases is automate the handling of the problem. There's a few things though that I think it makes sense to. You might not want to have an automatic response to. So for example, that failover situation, we've had enough. We've kind of experimented with auto failover and seen that we don't really want to put our failing from one data center to another totally without a human involved. So in those cases, I think it makes sense to script them and have them where it's easy for an engineer to kick off the process, but where it still involves a human actually making that decision and saying no, this isn't just a performance glitch. We actually lost the data center. AWS confirms data center dead. I'm going to do the flip, right? So in most cases, I'd agree, but in some cases, I think it does make sense to actually leave them under manual control. Does that answer your question?
Yeah. I just want to see if you have anything to add on that. I completely agree. It's more of a question of, how much do you trust these systems?
Yeah.
Do you trust the data that you're getting out of make that decision for you? So,
Yeah.
I agree.
Have you thought about, great talk by the way, have you thought about applying the active-active scenario to the data center level as well so that you have spare data centers online and serving actively so that you don't have to make the decision between manual data center level failover and getting it wrong automatically?
Definitely. That's actually something that we're looking to do. One of the reasons why we're switching to that kind of Cassandra and Zookeeper-based data store for our event dispatch pipe is that we actually plan to run Cassandra nodes in basically 2 Amazon regions, plus also a data center run by a third-party provider. And the idea there would be is that the loss of any single data center, in fact, is not going to knock your system offline.
Right. Yeah, that's great. Also, would you? I realize this is relatively new, but I know some of the RDBMSs, the SQL ones, some of them are starting to have proper synchronous master-master or asynchronous master-master replication. So your planning was probably before that started to happen, but any thoughts on whether that would be a viable option or whether NoSQL is always the way for this?
Yeah, so that's actually exactly what happened. We kind of started this work about a year ago, and at that time the semi-sync MySQL stuff wasn't out yet. We have actually though started experimenting with the Percona XtraDB, which is kind of an example of a clustered system, and that's actually been working pretty well for us. We're still able to kind of, from what I understand, I'm not actually working on this project myself, but there is actually still situations where the engineers have been able to kind of get it into corner cases where it actually does have problems. And the other kind of thing is, as I mentioned, the performance isn't as nice. Like for example, with, again, hopefully I'm not misrepresenting the product, but with XtraDB, it actually has to run at the speed of the slowest server. Whereas like with Cassandra, if you're doing quorum reads and writes, you're not limited to the speed of the slowest machine. You're just limited to the speed of the slowest kind of, majority subset. So.
All right, if there are no further questions, thank you very much.
Sure. Thanks.
All right, at this point, we're